/#walkthrough, TryHackMe Reversing ELF. ## executive summary. The Reversing ELF room introduces the fundamentals of analyzing Linux ELF executables without access to their source code. The objective is to inspect multiple crackme binaries, understand how they validate user input, and recover the required passwords or hidden functionality through static and dynamic reverse engineering. Unlike a traditional penetration testing exercise, the emphasis is on understanding compiled code and program behavior rather than exploiting network services. ##objectives. #analyze ELF executables. #recover passwords from binaries. #understand assembly-level authentication logic. #learn static and dynamic reverse engineering techniques. #develop a repeatable analysis methodology. ## methodology. For each binary, a structured workflow was followed. 1. Identify the executable format. 2. Extract embedded strings. 3. Execute the binary to understand expected behavior. 4. Observe runtime library calls where applicable. 5. Disassemble important functions. 6. Reconstruct authentication logic. 7. Test recovered inputs. 8. Validate successful execution. ##crackme1. ##goal. Identify the correct password. ##analysis. The binary was inspected and executed to understand its expected behavior. ##result. The correct password was recovered and accepted by the program. ##crackme2. #static analysis. The strings utility revealed useful information embedded inside the executable. ##result. The recovered password successfully authenticated. ##crackme3. #static analysis. Readable strings were extracted from the binary. Further inspection identified Base64 encoded data. ##analysis. The encoded value was decoded to recover the required password. ##result. Authentication succeeded using the recovered password. ##crackme4. #static analysis. Initial inspection with strings provided clues but did not reveal the complete solution. ##dynamic analysis. ltrace was used to observe library function calls during execution. The password comparison function exposed the expected password during the strcmp call. ##result. The recovered password was accepted by the binary. ##crackme5. ##initial analysis. Static inspection identified references to /atwa. /strncmp. /custom validation logic. The binary prompted for interactive user input. #disassembly. The check function was examined to understand the numeric validation routine. Further inspection of main revealed the expected comparison string used for authentication. #result. The reconstructed input successfully passed validation and produced the expected success message. ##crackme6. #static analysis. Inspection revealed a custom password validation function named my_secure_test. #assembly analysis. The function compared each character individually. Reconstructing the comparison sequence revealed the required password. #result. Supplying the recovered password resulted in successful authentication. ##crackme7.
##analysis. Disassembly of main revealed a hidden menu branch.
Rather than selecting one of the documented options, a specific integer value triggered hidden functionality. ## result. Providing the hidden menu option revealed the room flag. # #crackme8. # analysis. Disassembly showed that user input was converted using atois. The resulting integer was compared against the hexadecimal constant. Recognizing how signed integers are represented allowed the equivalent decimal value to be supplied. # result. The program granted access and displayed the final flag. ### techniques demonstrated. \ELF identification. \static analysis. \dynamic analysis. \string extraction. \runtime tracing. \assembly interpretation. \hidden code path discovery. \integer comparison analysis. ### key takeaways. This room demonstrates that effective reverse engineering is built upon observation, structured analysis, and incremental reasoning rather than guesswork. Simple command line utilities combined with careful assembly inspection are often sufficient to understand how many binaries perform authentication. The progression from straightforward string extraction to assembly-level reasoning provides a strong foundation for future malware analysis, software security assessments, and exploit development.